Hi guys, so this is the continuations of the previous lectures of the renal clearance. Okay, here we're gonna do a few examples of it. Okay, and if you see this, I got these questions from the Garden Hall and then pre-test book. Okay, and usually your questions are gonna look something like this. Okay, and they're gonna give you a bunch of numbers and they're gonna ask you to find, let's say, glomerular filtration rate, or they're gonna ask you to find renal plasma flow. Okay, and we'll do it right now here. Okay, so why don't we talk about this one right here? Okay, this person has urine flow rate of 1 ml per minute. His inulin concentration is 100 milligrams per ml, and his plasma inulin concentration 2.0 milligrams per ml, and he has a urea concentrations of plasma which is 2.5 milligrams per ml, and he has a urea level which is like 50 milligrams per ml, and they want us to find the glomerular filtration rate and urea net reabsorptions. Okay, so whenever we see this, okay, we always have to remember this. We usually use what? Inulin as your gold standard to measure GFR, right? So we have to figure out GFR first. And remember, what is our equations? Let's write it down in red. Remember, our primary equations is your clearance of the substrate is equal to, okay? So we can say this, okay? Your clearance of substrate is equal to your urinary, okay, of that substance times the volume, the urinary flow rate that represents your volume, divided by the plasma concentrations of the substrate. Okay, that it could be anything. This is just the equation that we can use for anything, right? It's just that whenever we use, let's say if we're using inulin, we're just going to make slightly changes, okay? Because remember, inulin, that gets filtered, okay, which freely and does not get reabsorbed, right? So the clearance of, let's write down, clearance of inulin is equal to, same thing with this one, U inulin, okay, this is U, okay, times the V, okay, of the inulin over the plasma concentrations of inulin, okay? That's right. And this two number, the clearance rate we're talking about, okay? Because we're talking about the time, okay? The clearance rate is inversely proportional to the plasma inulin, right? So whenever we talk about this, let's say, even I can use this clearance inulin as the indicator for GFR. So instead of writing clearance of inulin, I can write down GFR times plasma of that inulin, okay, which is equal to your urinary inulin times the volume, okay, and this GFR times plasma we call them as filtered load, and this U and inulin plus volume we call them excretory load, or you can say filtration rate, and then, right, this is what filter load and excretion load basically means, right? Whenever there's a rate is used, we're talking about the time, okay? Now if you come back here, okay, let's use these equations, okay? So we're trying to find the, okay, GFR, right? So GFR is equal to, or clearance of inulin is equal to, what is my urinary concentration of inulin? If you come back here, what is that right here? It's 100 milligrams per ml, okay? So we'll write down 100 milligrams per ml, okay? Then you multiply this by, what is my urinary flow rate right here? It's a 1 ml per minute, okay? That is what it is. You divide that by, what is the plasma concentration inulin? It's given right here. It's 2.0 milligrams per ml. This unit, this gets cancelled out, right? So what do we get? 100 times 1 is 100. So you divide by 2, what is that going to give you? Your GFR should equal to 50 ml per minute. That means this person has what? He has a kidney problems, okay? Because his glomerular filtration rate has decreased. In this case, right, the inulin is not filtering much, okay? That means there is probably accumulations of inulin. I mean, not inulin in a precise condition, probably creatinine, okay? Because we could use this as a creatinine too, okay? Now, this is my GFR, okay, for the inulin. But they also want us to find the urea net reabsorptions, okay? Remember what net reabsorption means. Meaning that whatever that got filtered load, okay, that filtered out, okay, we'll just talk about this quickly right here, okay? Here, look, this is my glomerular, right? And this is Bowman space and all that. So whatever that got filtered out, right? Okay? Filtered out, okay? But it does not appear on my urine, okay? So reabsorbed because all the substance got reabsorbed, okay? So that means whatever that filtered load was, okay, that wasn't able to appear in the urine, or a lot of those got reabsorbed, okay? So in that case, we have to do reabsorptions is equal to what? Is equal to filtered load minus, because remember, it got filtered, okay? What are the substance that loaded here on the glomeruli that got filtered? That's what we call the filtered load. Then when it comes to the urine of that substance, okay, it did not appear in the urine, or it less appeared because most of them got reabsorbed probably, okay? So that's why we have to say filtered load minus excretion load, okay, in order to find the reabsorptions of that substance, because this is what we're trying to figure out. And it's really important that you understand this, because remember, urine formations are processed of three things, okay? Glomerular filtration rate, reabsorption, so glomerular filtration minus the reabsorption plus the secretions, or glomerular filtration rate plus secretions minus the reabsorptions, okay? This is how, that's the urine formations, okay? And we're basically doing that. So now, if you come here, what is my filtered load is? We said filtered load is my GFR times my plasma of that inulin, right? That's what we're talking about, right? So what is my GFR here? We use the GFR. My GFR is what? We got what? 50, right? So we do 50 ml per minute, okay? But remember, we have to do, because right now we're trying to find the reabsorptions. What? We're trying to find the reabsorption of urea reabsorptions, right? So we got the GFR by using the inulin concentrations, but remember, we're trying to find the net reabsorption of the urea. So we have to look at what is the plasma concentrations of urea, right? So if you look at that, it should be given. It says 2.0 milligrams. So you just do, this is my GFR. Okay, let's just write down. Okay, let's write down. So your GFR, okay, times, okay, your plasma concentrations of urea, okay, minus, okay, your urinary concentrations of urea times the volume, the urinary flow rate, right? So my GFR, we got it using the inulin, 50 ml per minute, right? You multiply that by, what is my urea? If you come back here, plasma urea, it's 2.5, okay, which is milligrams per ml. Then you do minus, what is my urinary urea right here? 50 milligrams, right, per ml, and times my, what is the flow rate, which is 1 ml per minute, right? So when you do this, what is 50 times 2? That means 125, right? 125. And what is 50 minus 50 times 50? So you should be able to get 75. Your 75 is what tells you about 75 milligrams per ml. This is the net reabsorptions of the urea. And this is how you calculate the net reabsorption of the urea, okay? And this is something equations you should remember too, okay? Now, after this, let's come back here. This is another patient here, okay? The 68-year-old woman with the hypertension, okay? With the oliguria, okay? And then the CT shows the hyperplastic of the left kidney, okay? And then they want us to find the estimate renal plasma flow, okay? And they give us a bunch of numbers, like they give renal arterial PAH, which is 6 milligrams deciliters, right? Renal vein they give you, okay, renal vein of the PAH actually, they give you 0.6 milligrams per deciliter. Urinary pH, they give you 25 milligrams per ml. Also, they give you urinary flow rate 1.5. And they also give hematocrit. But they're trying to find the renal plasma flow. Do we need all that information? Probably not, right? Because remember, renal plasma flow, we use what? The aminohyperic acid to estimate the urinary plasma flow, right? So all we do is look, same equations here, right, guys? So we do the clearance of, let's say, pH is equal to, we do, okay, the urine pH, okay, times the volume over my plasma of pH. Let's just do that. So clearance of the pH is, and we're talking about renal plasma flow, okay? Because that's the estimated plasma flow. What is my urinary pH? They give you my as 25 milligrams per ml. That's what they give you, right? Now, what is this? They give you flow rate as 1.5 ml per minute, correct? Now, divided by, what is my plasma of my urea? Renal plasma right here. Urea on the arterial side. not on the vein, okay? That's a 6 milligrams per what? Deciliter. Look, this is the key concept here. This unit has to be the exactly same, okay? The ml and deciliter, okay? So 1 ml is equal to what? 0.1 deciliter. So if I do the math and convert into this, would be 0.6, right? That's what it will give. So when I do CA, PAH, do that, 25 times 1.5 divided by this 0.6, you should be able to get. Let's just do quickly, okay? Quickly do this. So you have a 25 times 1.5, okay? So 0.06 it should be, right? 25 times 1.5 divided by 0.06 it should be, because this should be, because if you change the deciliter to milliliter, it should be 0.06, okay, divided by 100. So that's why you should be able to get. So that will be able to give you 625, okay, ml per minute. This is the estimate. This is the estimated renal plasma flow, okay? This is estimated, guys, which does not mean it's a true numbers, okay? It does not mean it's exact number, because if you want to find the renal plasma flow, we have to do something else, okay? Because this is an estimate, okay? That's what it is. If you want to find the true estimate, there's a process we can do. Let me erase this, okay? If you want to find a true renal plasma flow, then we have to do what? We have to so-called as total, okay, renal plasma flow is equal to, okay, let's write down. They call this as, okay, because this is on clearance, right? This is what we found in the urine, right? So that means we have to do so-called as, okay, your clearance, okay, your PAH clearance, okay, over your extraction ratio. What does this mean? Your extraction ratio basically means is that, this is important, the percentage of that PAH or the substance, for this case your PAH, that got removed or excreted by the kidney, okay, the percentage. And normal condition in a steady state, it's about 90% is what does get excreted out when we're talking about the PAH, okay? That's what it is. Because remember, if we quickly, when I erase this graph, but this is a Bowman capsule, right? Whatever that got excreted down here, right? So basically that's what we're talking about, right? But some of them does get to the, so if the 90% gets excreted out, then 10% you do get to see in the renal vein, okay? That's what it is. So there is the extraction ratio we can find out, okay? An extraction ratio we can find out by doing two things, okay? Okay? One thing is that, let's write down the extraction ratio, okay, is equal to, we have to figure out, okay, let's just quickly talk about it. Okay. And then this is the, okay, look, if you come back here, okay, we have to do, what about the arterial side is, what is the concentration of the PAH? Let's just write down, okay, the arterial side, okay, we'll write down the artery of PAH, what is that, what is the PAH concentration, the arterial side, okay, from here, minus the, what is the concentrations of the PAH under my venous side, okay, venous PAH, divided by this one, the arterial PAH concentrations, okay, and that will be able to give you extraction ratio. And remember, we have given here my arterial side, they said 6 milligrams, all right? If you come back here, look at this, they're given you, okay, right here, and then there, right here. So the arterial side, they said 6 milligrams per deciliter minus, right, my vein, what is they give? I get 0.6 milligrams per deciliters over, right, let's just do this, over my arterial, which is 6 milligrams per deciliter, and ratio is not going to have any unit, right? So when you do the math, look at this. What is going to be 6 minus, okay, 0.6 divided by, you have a 6. That will give you a 0.9 or 90%. Remember how I said? Okay, now, if you come back here, Okay, let's use this. In this equation, let's plug it. My pH clearance is what? It was 625 ml per minute, right? Divided by my extraction ratio is 0.9. Okay, what is that going to give you? 625, okay, I'm using a calculator, divided by 0.9, that will give you 694.4 ml per minute. And this is my total renal plasma flow, or you can simply say it is a true renal plasma flow, and this is how you can calculate the true renal plasma flow. Normally they may not ask you, but I just wanted to let you guys know. Estimated is about 625, okay, but it's a true renal plasma flow, okay. But remember guys, they did one more thing. They also give you the hematocrit, okay. Let's use those and let's talk about this. Why they are trying to do? Maybe they're trying to figure out what is the renal blood flow, okay. Let's talk about this, okay. So renal blood flow, if you remember, is equal to what? They say, what about the blood is coming down here, okay? And how much that it get excreted out. So in order to do that, we have to do renal blood flow, we have to know renal plasma flow, and we do know that, over 1 minus, let's say, hematocrit. Okay? That is what it is, renal blood flow. That's what my hematocrit is. So if we do the renal blood flow is equal to what? For let's say renal plasma flow, for our case, we'll say we can use this one or this one, either one. We'll just use 625 for now. So the ml per minute over 1 minus, what is my hematocrit at 40%? 0.40. That means 625 divided by, what is this called? 6 divided by 0.6, right? So when you do that, your 625 divided by 0.6, that gives you 1041, okay, ml per minute. This is my renal blood flow. That's how you calculate renal blood flow, okay? That's what. And if you use this number, okay, we can do that too. Yes, so which is a true number, 694 divided by 0.6, about 1156 ml per minute. That's what you get, okay? And this is how you can calculate the renal blood flow, okay? So we use all this number to calculate the renal blood flow, okay? Now, after we do this, I do wanna tell you something, which is called clearance rate, okay? Because every substance has different clearance rate, okay? And one thing that I need to quickly talk about is that, let's talk about, you guys know that, like for example, those tubular fluid over plasma thing, right? And this is like, let's say this is like a sodium or something, right? A water, about the same proportion they get reabsorbed, right? So this would be about 1.0 right here. Let's say 1.0 right here, right? But remember, you have seen graphs like this, like that. This would be probably glucose or amino acid, or maybe this would be like your bicarb, right? You have seen that kind of. And here, right here, this would be like your PAH. We just talked about it, right? Because it gets secreted. And this is probably going to be what your probably creatinine rate right now. And let's just write down your inulin right here. Okay, maybe write down like potassium right here. Okay, like that. Okay? Because you do see more pH, creatinine, inulin, or potassium in your urine, okay? And then comparing to like glucose and amino acids. So whenever we see this graph, we have to compare the clearance rate, okay, into this compound. Because remember, when you see the glucose, what is the clearance rate of the glucose? Is 0, because you do not see any glucose or amino acids in kidney, okay? So because of that, what happens? The clearance rate is 0. That's what it is, right? So when we come here, we can simply say that the clearance rate of PAH is greater than the creatinine clearance, okay? Because which is about what? 140 milligrams per ml per minute, I think, creatinine clearance, right? And this creatinine clearance is greater than your inulin. Remember, because inulin does not get reabsorbed, does not get secreted. But because creatinine gets slightly secreted, because of that, what? The clearance rate of the creatinine is higher. And this pH, the 80% of creatinine, this pH gets secreted from the proximal tubules, okay? So that's why this is really high. So pH is higher, we're writing the clearance, we're talking the clearance rate, okay? Higher than creatinine. Creatinine is greater than inulin. Inulin is going to be higher than, let's say, potassium, right? Remember, because you do see more potassium in there. And the potassium clearance rate would be higher than, we can simply say, sodium. And sodium clearance rate would be higher than bicarb. Remember, 80-85% of bicarb get reabsorbed. And then bicarb creatinine clearance rate would be higher than obviously your glucose. Because glucose you see 0, and inulin you see about like 120 ml per minute, okay, something like that. And this glucose would be like 0 because everything else get reabsorbed on there, okay. So this is how you can say that, you know, you can tell about the clearance rate too, looking at the different electrolytes, okay, or even non-substances like PAH or inulin, even creatinine, okay, even there's a glucose or even amino acids, okay. This tells you about the clearance rate, okay. This is what I wanted to quickly touch on you guys. All right, guys, I hope I made it very clear to you guys about the renal clearance. This is very, very important physiology. I really hope that you guys spend extra time understanding about this clearance, and especially knowing the equations, okay, and doing like bunch of problems. All right, thank you very much, and please hit the subscribe for me. Thank you.